Hey everybody. So this is the second of two re-recordings because of some technical issues. So this one we're going to talk about all of the primitives. So starting from literals and operators through to arrays and slices. In the original, I got stuck on something. So now I know the answer before I get stuck. So, it's going to go a little smoother than the original. But, I'll try to keep it approximately the same level of discovery. All right, so let's see. Primitives. We have primitives, signed integers, unsigned integers, floating point numbers, F32 and F64. Oh, U128. And U size, which is pointer size, and I size, which is pointer size. Now, it's unclear what U size and I size are. Presumably they are specific to the particular platform that we're running on. Should be interesting. Because, sometimes U size and I size are going to be larger than some of these, and sometimes they're going to be smaller, maybe. Because if this is just like whatever a pointer is, then, like I said, I assume that the pointer can be different depending on the platform you're running on. So, but generally speaking, on modern systems, it's going to be a U64 probably, because that's going to address, umpteen gigabytes at least of memory space, and that's probably more than we ever want. U128 is kind of unusual. I don't see that very often. So in C#, for instance, there's a long and an unsigned long data type, which is the U64, and just int, which is the U32. So that's kind of the standard thing. I32 is kind of the normal size that we typically work with and databases work with and that sort of thing. But U128, well, first of all, I don't remember in SQL there being a data type that would store 128 bits of data. So that could make it interesting to try to store that in a database table. And since most of our processors are 64-bit processors, we're also going to have some, I assume there's some interesting stuff going on in the background to actually do the math on 128 bits. But that's not unusual. I mean, back in the day when we had 8-bit processors, we still did 16-bit math. It was just, a little trickier to do. Floating point, F32 and F64. So F32 would be in a C# float. F64 would be the double. Just a little bit of a side note. Do not use these for money. If you need to, if you're in the realm of Apple type dollars, you might want to use the I-128 to specify, and then multiply by 100 or 1,000 or whatever to get to get your 3 decimal places. So work with pennies or fractions of a penny. And then when you want to, the very last thing you do before you go to display it to somebody is divide by whatever, 100 or 1,000 or whatever it is, to display the, excuse me, the pennies, dollars and cents that you want to work with. And that's a fairly common thing to do. In C#, just as an example, in C# you would use the decimal data type for dealing with money. But in that particular case, it's actually an F128. So, then rounding errors are far off into the distance. Anyway, all right, so we've got char, Unicode scalar values. So they're 4 bytes each. That's interesting. Unicode, sure, Unicode values can be 4 bytes. More typically, they were 2 bytes. But then there's UTF-8, which is a variable length. But I guess 4 makes the most sense because then we have a standard size for each character, which is important when you're trying to figure out the length of a string in a very convenient kind of way, right? Because you can take the number of bytes divided by 4 and say, okay, that's the number of characters in this string. If you had a variable length strings, then you'd have to parse the string each time you wanted to figure out its length, or you'd have to store the length as part of the string. And I assume they didn't want to do either of those things, so we just stick with 4 bytes per character. Boolean, true or false. It's interesting, it doesn't specify how big a Boolean is. And the unit type, the brackets. We've run into this last time because a return value, there was an error message where it said the return value of your function is bracket bracket. This is a empty tuple. So we don't know what a tuple is yet, although I see 2.2 is going to talk about tuples. So we'll find out what a tuple is shortly. Despite the value of the unit type being a tuple, which will be explained, it is not considered a compound type because it does not contain multiple values. Cool. So a tuple, I guess, is typically a compound type from this description. All right, compound types. Oh, there we go. Arrays like 1, 2, 3. Tuples like 1, comma true. So it looks like a tuple is, we use the same word in C# when we're describing this kind of ad hoc object where you can throw in a bunch of things, comma separated things into an object surrounded by round brackets, and you return that. It's kind of a way, the way I use it in C# is to return, to allow multiple return values from a function or a method, because otherwise you would, typically you would only return one thing, but this one thing can be a tuple, and then you can stick a bunch of different data types into that tuple. And arrays are the obvious thing, square brackets, like every other language uses square brackets to indicate arrays, commas to separate the array elements, and all the elements have to be of the same type, I would assume. Okay. Variables can always be type annotated. Numbers may additionally annotated by a suffix. Okay, so 5i32, we can specify exactly what we mean. So which kind of integer we're talking about. Here, the floating point number, (f64), we're specifying that the variable is that type. And then this would be coerced into an f64. I assume that by default, if we didn't specify that, would end up being an f32, I guess. Boolean, we can specify the Boolean, although I probably don't need to specify that. Yeah, here we go. Or the default will be used. So, f64 is the default. Interesting. Okay. The default float is f64, not f32. And then, but the default integer is i32, which is pretty standard. This is a bit unusual, but okay, why not? So what it means, I guess, basically is that you're going to use the f64 floating point, the larger expanded floating point, unless you have a reason not to, and then you'll specify f32. Inferred type. Okay, inferred type. What's going on here? A type can also be inferred from context. Okay. So here, let mut mutable inferred type equals 12. So that would fit into an i32, and that's the default. But what this is saying is this is actually an i64 because down here, later on in the code, we assign an i64 to this. And we made it a really big number. Let's see. 4 billion and change. And yes, 4 billion, and that's just a bit bigger than, well, actually, an I-32 goes from plus or minus 2 billion and change. So 4 billion and change definitely requires a 64-bit signed value to specify. Actually, it probably only requires 33 bits, but we're over the 32-bit boundary, so now we're, or 34 bits probably. So now we're up into the 64. We have to move up one level. Okay, but mutable variable can be changed. If we specify something as mutable, then we can change it, which I guess we just did up here. Mutable equals true. The type can't be changed. So mutable was 21. Now we set it to true. So this is different than JavaScript, because in JavaScript, everything's just a variable. And, you know, you can replace a decimal number with, you can replace a floating point number with an integer. You can replace an integer with a Boolean. You can replace all of them with an object, you know, or an array or whatever you want to do. So with JavaScript, you're really flexible on what a variable can contain, and that leads to problems if you actually do that. Generally speaking, that's frowned upon, but the language does not disallow it on its own. You have to police yourself if you want to make sure that that actually happens. Here, the language is going to police that on our behalf and let us know, sorry, you can't change the data type. And so this is like, this is a strongly typed language, so C#, Java, those kind of languages also enforce this. So this is not unusual, unless you've only written code in JavaScript, then this would be weird, but otherwise, no. Now this one here, variables can be overwritten with shadowing. That one, yuck, I don't like that, because even though you can't change the data type of the existing variable, you can create a new variable with the same name and give it a different data type. Boy, that's not something I like. In C#, for instance, you'll get an error. You won't be able to do this because it'll say, nope, you've already used that name for something else in a different context. You cannot change the name or cannot reuse the name here. And honestly, I mean, that saved me a bunch of in a bunch of situations where the method or function is getting a little complex, and I go to use a variable and I didn't realize that I'd used it before, and I go, oops, okay, yes, I need to pick a different name. But here, it would just let me do it. And then if I wanted to refer to the original data somewhere further on, then I have problems. So that's not a big fan of that. But, I don't know why you'd even allow that. All right, anyway, so that's kind of an interesting opening salvo here. But we're not going to play around with any of this. We'll play around a little further on. All right, literals and operators. What have we got here? Integers, floats, characters, strings. Okay. And characters have single quotes, strings have double quotes. Again, this will be a little different for the JavaScript people or PHP people in that this should be familiar to Java and C#. Single quotes means character, double quotes means string, but they're separate things. A character is going to be a single character and never going to be more than one character, right? So you can't then assign a single quotes a to a variable and then assign ABC to that same variable, because it'll say, nope, that was a character, that's a string. They're not the same. because these can be expressed using literals. Integers can be expressed using hex, octal, or binary notation, like this. Who uses octal anymore? I mean, honestly, I haven't used octal since the days of the PDP. But, okay. I suppose it comes in handy for somebody somewhere. But typically, hex, and octal is just for those people who don't know, is a 3-bit notation. So hex encapsulates, each character in a hex string encapsulates 4 bits. And obviously in a binary, each character is expressing 1 bit, so it's either 0 or 1. And here, because it's expressing 4 bits, it's the range of 0 through 9 and A through F. If you count those up, you end up with 16 different symbols. So 16 different symbols, 4 bits, for 2 to the 4th power is 16, so there you go, your 16 symbols. Octal is 3 bits, so you can express 0 through 7. So the numbers you can use are 0 through 7 and then 0 through 7. So each digit is the numbers 0 through 7. And again, if you think in terms of bits, you can express, you can kind of more compactly express some bit pattern. But honestly, I know I've always thought in terms of hex, so I can visualize, A, for instance, is 1010, 9 is 1001, etc. So if you give me a hex string, I can kind of picture in my mind the bit pattern. Octal, I mean, obviously I could too, because octal is a subset of hex. So, the numbers 0 through 7 is, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. But all if you notice, everything is powers of 2, right? All our bits are I32, are I8, are I16. So why you'd express something in octal when you're going to be sticking it into a power of 2 data memory space? Not quite sure, because 3 bits really, doesn't line up. So anyway, but okay, fine. Maybe for completeness. Underscores for readability. So instead of a comma, you can stick an underscore to specify. I guess you can do it on the other side of the decimal as well, which we don't normally put commas on that when we're writing things out, but it gives you the ability to count zeros more easily. Now here we traditionally use 3s, right? Tens, hundred, thousands, so we count them in groups of 3s. Yeah, but okay, so there's our octal. There's 3 bits. I don't know. We need to tell the compiler the literals we use. We use the U32 suffix to indicate whether the literal is unsigned I, so it's signed, fine. Operators available when their precedents in Rust are similar to other C-like languages. Okay, so plus, minus, double ampersand, 2 vertical bars for or. So this is and, this is or, this is the not. These are bitwise operations and or exclusive or, shift, right. Okay, so there's nothing surprising here. We're going to go plus, minus, times, divide, and the mod operator, the percent sign, the mod operator. Try changing I32 to U32 to see why this type is important. Okay. So 1, okay, actually that's kind of fun. Well, we can do that. The one thing I want to point out, so this says short-circuiting Boolean logic. Okay, so what do they mean by that? What they mean is, and this is true of all the languages, so this is not, I mean, if you're used to these languages, it's not surprising, is that if in an AND situation, both sides have to be true for the expression to be true, right? True and true equals true. If you do a truth table, then any other situation, if there's a false on either side, then it's false. So what that means is that the compiler, or when it's executing, it can take a shortcut. It can say, well, if the first side of the equation is false, then I don't need to evaluate the second half. Right? So if this were false, then I don't need to evaluate this, because it's going to be false. No matter what the second half says, I know the expression is going to be false, therefore I'm just going to evaluate the first side and return false. In the OR case, the truth table is if any of them are true, then it's true. And so again, you can take a shortcut. You can say, well, if the first half is true, I don't need to evaluate the second half. So it's kind of the reverse, right? So in the AND case, if the first half was false, no need to evaluate. In the OR case, if the first half is true, I don't need to evaluate the second half. And so if you've written any idiomatic JavaScript, you can take advantage of this in not in an if statement, but just in a regular thing to assign a value, right? So you'd write let x equals something that could be null or falsy, in JavaScript terminology, or some default value, right? And so if the first half is false, then it's going to evaluate the second half and return the default value and assign that to your variable. So, this is not that surprising. It shouldn't be that surprising that this is the behavior. Not, of course, just reverses the thing. Now, bitwise operations, where you use the single ampersand or the single vertical bar or the single, well, actually, I don't think there's a double exclusive or. If you use a single one of these, then it does evaluate both sides always, because what you're saying is, I want the result of the ORing or ANDing or exclusive ORing of the two sides. So it must evaluate both sides, exclusive or do the operation on them, get a set of bits, and then evaluate that for truth or false, or true or false, or some to compare against some value. So again, some people, I've seen some students of mine think, especially in C#, that because the behavior of a single ampersand and double ampersand looks like about the same, because if you have a Boolean and single and a Boolean, then it'll merge, it'll compare those two Booleans, it'll AND them together, and then return a Boolean. It looks like it's behaving the same way as the double ampersand. And so in most cases it will, but it's got this side effect, that short circuit side effect. And if you're expecting that, or if you're not expecting that, you're going to get some, things go wrong potentially in your code, and you won't really see it, because this is actually hard to spot. This is the double ampersand versus the single ampersand. Sometimes it doesn't really stand out that well when you're writing code, especially something more complex, and then you'll end up in a situation. So if you mean to do comparisons for the sake of evaluation, use the double. If you really want to do bitwise operations, if that's what you're doing, If you actually want to know the result in terms of the bit patterns that come back, then use these and only them. All right, so then the other thing we have is the shift left, shift right business. And then we've got just to show you that you can use the underscores. Yeah, okay. So, no, I'm not gonna. Oh, I guess the one thing I was gonna say is, so this to-do thing here, try changing the I32 to U32 and see what happens. Okay, here's the deal. Bit patterns, so in an assigned integer, all ones is -1. So if you think about 32 bits, if all 32 bits are ones, then that is the smallest negative number, -1. If they're all 0, then you end up with 0. And if you end up with 1, like in the lower order bit, there's just a 1, then that is the smallest positive number. So now think about that. So we've got 1, we've got 0, and then we've got all ones, meaning -1. So if we did a signed integer subtraction of 2, from 1 minus 2, then what it's going to do is it's going to subtract, so the 1 minus 1, it gets you to 0, minus, so if you have zeros and you subtract 1 from that, you get all ones. So, in a signed case, that's -1. But in the unsigned case, you still, when you subtract 1 from 0, you still end up with all ones, but because you've overflowed. But when you do that and you interpret it as an unsigned integer, what you end up with is the largest integer. So you end up with 4 billion and change. So, and that's what they were trying to show here, is that you're either going to end up with -1 in the signed case or 4 billion and change if it's the unsigned case. And that's completely normal because of the way computers and math work, right? You only have 32 bits. And so it's possible to overflow the bits. I used to do this a lot with 8-bit values. You'd count down, even 8-bit values. So you'd end up with, we could do it with 4-bit values, like, 15, 14. So 15 is all ones. 1, 1, 1, 1, 1, right? 15, 14, 13, 12, 11, 10, 9, down to 1. And then you get to 0, and you subtract 1 more, and that takes you back to all ones. So you're back to 15. And so you can loop repeatedly over some things, but just keep subtracting, and you'll end up with, 15, 14, 13 down to 0, and then 15, and then back down to 0, and then 15, and then back down to 0. And, that's a useful thing in certain circumstances. Whenever you see somebody create a table where they've got alternating colored lines, generally that's what they're doing. They're doing a subtract 1. Oh, it's a 0. Okay. And so they've got a 1-bit value that they are subtracting and subtracting some more, and which causes an overflow, which then subtracts, so you kind of, or adds or whatever. So you can adding does the same thing, right? Because if you were going in the other direction and you had all ones and you added 1 more, you end up with all zeros. And then a 1 in the next order bit, but that next order bit doesn't exist, so you just overflow and back to 0 again. In most processors, there's an overflow bit that you can check, and you can go, oh, okay, the result of my math was this number, which is stored in my register, and also there's an overflow. And so, but you can ignore that too and just say, well, that's cool. I don't care. I intended to do this. But in any case, what's going on here is pretty standard stuff as far as calculations are concerned. So, it's not something you run into a whole lot, but There you go. All right. Let's move on to something. Tuples. Okay, tuples are kind of cool. What is this? Tuple is a collection of values of different types. Tuples are constructed using parentheses, and each tuple itself is a value with a type signature, where T1, T2 are the types of its members. Okay, so here, we've got some interesting, and we've got activities. All right, let's take this one. We'll copy this. And let's go here. Oh, I've still got the old one here from last time. So let's close this folder. Let's create a new terminal. /rust. Okay. Cargo new tuple2. Okay, and we're going to file open folder Rust tuple2. Oh, I didn't mean to double click that. Tuple2. Select folder. All right. Go to main. Select all, Control A, Control V to paste, and there we go. All right, and let's run this just to see what happens to make sure. Oh, we should save this and run this. Okay, so what's going on here? We've got long tuple first value, long tuple second value, tuple of tuples. Pair is 1 true, the reverse pair is true 1 element tuple, just an integer 5, hello, hello, matrix. Okay, cool. So that's the kind of stuff it produces. So it looks like we've got a function called reverse, and it will reverse an I32 bool tuple, and it will return a bool I32. Okay. So okay, and then we're going to create. So we've created. All right. Okay. So and pair is the I32 bool tuple that's being passed in. So pair, and then we're going to assign pair to this tuple that we created here, and then we're going to return a new tuple with these parameters reversed. Okay. Interesting. Let can be used to bind the members of a tuple to variables. Okay, so what we're doing is we're kind of exploding up the pair into 2 different parameters that we can access, and then we're creating a new tuple with the parameters reversed and then returning that. And as we've discovered, right, that we could write this as return semicolon, but and get the same effect, but the kind of the idiomatic way of writing it in Rust is to just say, here's the object I'd like you to return as a statement. Well, not even a statement because it's not ending in a semicolon. It's the last thing that we're doing, whatever terminology. I'm not sure what the terminology is. They probably told us, but I don't remember. Okay, and then we've got this matrix, and we've labeled it with the derived debug so that we can, I guess that was the debug output thing, I think. And this matrix is going to be for F32 floating point values. Okay, and then we've got a long tuple. Long is in lots of different values tuple. And so we've got a U8, a U16, a U32, a U64, an I, and then a couple of floats, a character, and a boolean. And I suppose we could finish it with a string here. Now, this is interesting. long tuple dot 0 long tuple dot 1. I think did we not encounter? No, I guess we didn't. So we can refer to the tuple elements with this dot 0 dot 1 syntax. And then we can create a tuple of tuples. So each element of a tuple can itself be a tuple. Okay. Tuples are printable. Tuple of tuples, the debug, and it's going to print that, and it printed that here, tuple of tuples. There we go. It drops all the data type stuff. So 1, 2, 2, 1, 2, 2, 4 minus 1, 4 minus 1, minus 2, minus 2. Okay, so yeah. Long tuples more than 12 elements cannot be printed. Okay, let's uncomment that to see the compiler error. Okay, save. Oh, too long tuple. The trait debug is not implemented for integer. Okay, so it would appear 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it would appear that what they're doing is they're doing some kind of overload on print, and it's expecting up to 12 and no more than 12. Okay. So it looks like you can print 1, you can print 2, you can print 3, you can print 4, etc., etc., but you can't do more than 12 because the overload doesn't allow that. Presumably, we could create our own implementation of the display, right? We could, the display trait, if I'm using the terminology correctly, and then we could do it ourselves, but the default built-in stuff won't allow it. Okay, so we got pair, 1 true, the pair is, the reverse pair is, reverse pair. And that was the method we looked at, or the function we looked at the beginning, which you pass in a I32 Boolean, and you get back a Boolean I32. Okay. Okay, to create one element tuples, the comma is required to tell them apart. Right, because here we had to specify, so a one element tuple has a comma. This is just an integer with brackets around it. So the brackets are not necessarily interpreted as a tuple. You need that first comma to say this is a tuple, because otherwise it's just round brackets around things, which we can do, which we can group things by putting round brackets around them. Typically you would use the round brackets in a situation where you wanted to adjust the order of operations in a string of calculations, right? So because it's bed mass or ped mass, brackets or parentheses, whichever you want to do, come first, right? So anything in brackets, you do it first, and then after that. So the brackets, we would, this is interpreted as, oh, you just put brackets around an integer. This says you've created a tuple with one element in it. And you can see that here, one element tuple, 5 comma, just an integer, 5, right? So it's one or the other. Tuples can be used to destructured to create bindings. What the heck's a binding? Oh, I see what this is saying. Okay, so if we have 1 hello 4.5 true, then then we assign that to tuple. So we have a tuple. So this is just kind of setting up the example. We have something called tuple. Now we can assign the contents of tuple to A, B, C, and D, and then we can reference them individually. And this is not that unusual. This is, I mean, in C#, using tuples in C# works exactly the same way, that we can give them all names and then use those names. And then matrix, we'll pass in a matrix and we print the matrix. There's the matrix. Okay, so now what? Oh, I know. So this reverse thing here, because I was curious about this. So this 0.0.1 syntax. I suppose we could also, can we do it this way? Because if we have pair, then we say pair dot 1 comma pair dot 0. Can we do that? Save that and run that. Pair is reverse is true 1. Yeah. So we didn't really need to do this stuff, although I mean I guess it's kind of cool to see the destructuring, but then they gave us an example of the destructuring, a better example of destructuring down here, so really there was no need for that, but this is kind of cool. Now this 1 and 0, I wonder if we can do something like let x equals 1 and then say pair x. No field x on type. No. Okay, so no, he wants a name. It wants a name. So we could, but we don't have named things. So basically, the name is 1. Okay, so I'll save that. All right. So that's another way of doing this, based on what we saw down there. All right, and long tuple, tuple of tuples. We don't ever really print the long tuple. So yeah, I added this thing here to the end, but it, that's an ampersand stir. Interesting. That's an ampersand stir. I don't know why, but okay, cool. I don't know what that means yet. Right, but this hello is also an ampersand stir. Okay. All right. Interesting. All right, so we have an activity. Let's see. Let's go check out the activity. All right, what do we got here? Recap. Add format display trait to the matrix structure in the above examples that you switch from printing the debug format to the display format. You see the following. Oh, so I want it to look like this. 1.1, 1.2, 2.1, 2.2 with round brackets. Okay. So let's go back to there. So let's see if I can remember how to do this. So we want to do impl display for matrix. Oh, and I think I want to go back to, I think I want to use std colon, double colon. Okay. that's not right. I don't remember. I do not remember. All right, let's go back and have a look. Let's see what the syntax is. So back to hello world, formatted print. There it is. Used in form. Right. Yeah. So let's grab this line. Back to here. We'll use it here. Okay, and then back again. We're going to grab where to go. Oh, here. Oh yeah, it's 4. I did that right. But I want this line. Copy. And inside here, a curly bracket to match. Okay. And you're going to complain because I don't return anything. That's what you're complaining about, right? Yeah, expected result, didn't get one. Okay, so write hello. Okay, so that's going to do that. Okay, so instead, what I want to write is round bracket curly brackets, space, curly brackets, round bracket, and I want to say self.0, self.1, and then question mark semicolon, right? Because we're going to do a second line. Right. Well, basically the same thing again. Except this time we're not doing that, and it's 2 and 3. Is that right? Yeah, maybe. Yeah, I think that's right. All right, so we'll save that. Oops, what's the problem? What's the problem? No method named write format found in the reference static stir in the current scope. What? No method name write format found for reference ampersand quote stir, static stir. Oh, right. F. Forgot a parameter. Okay. That's a weird error message for you don't have enough parameters. Although I suppose because this is a variable number of parameters, then they can't really tell that I don't have enough without parsing inside here. And it probably does that much later on. So it's trying to interpret this as if it were a formatter and going, I don't understand what kind of formatter this is. Okay. Okay, I'll forgive it. But it was a little kind of off-putting. Run this. Okay, so we end up with... we end up with nothing because I didn't change this. So let's get rid of that. And we'll run it again. All right, almost 1 1 1 2 2 1 2 2, but E wanted a line break. Can I say right line? Yeah, I can say right line. Let's try it one more time. Okay, there we go. There, that's perfect. I think that's what the thing asked for. Oh, wrong place. Primitives, tuples. Oh, well, other than the extra space here. But I think we can live without that. Okay. Add a transpose function using the reverse function as a template, which accepts a matrix as an argument and returns a matrix in which the two elements have been swapped. Okay, so matrix, transpose matrix. Okay, so let's grab these two lines of code. Copy that. And bop that over here. And we'll just replace this. And transpose doesn't exist. Fair enough. Matrix, matrix, arrow, matrix. Okay. So we have a matrix and we want to swap the, well, transpose function, right? So we want to swap the, so basically we want to swap this one and that one. So we want to swap 1 and 2. So instead of doing 0, 1, 2, 3, we want 0, 2, 1, 3. And it looks like, because matrix is a tuple, right, because it's got the round brackets, so it's a tuple, that we have to use this syntax or this syntax. So let's try this one, the one they used first. So we would go let L2, L3 element, that's my short form for element, equals matrix. Okay, and then say return L0, L2, L1, L3. Oh, not that. No semicolon there. Okay, let's try that. Save that. Ooh, no, complaint. What are you complaining about? Mismatched types. Expected struct matrix found tuple. What? Oh, hang on a second. Oh, struct matrix. I don't really get it. It's 2 implementations. What's going on here? So a matrix is of type matrix, not tuple. Oh, so I'm misinterpreting that. I assumed that because of the round brackets here, I was just creating a named tuple, but I'm not. So I can't actually, so what this is saying is, hey, okay. So what if I did this? Matrix dot 0, matrix dot 1, matrix dot 2, matrix dot 3. Okay, and then what's? Okay. So then, let m equals, I use semicolon, return m, or can I just do m? Is that working? So let's see if I understand this correctly. So I have a matrix. I take the matrix and I convert it into a tuple. And then I create, and I take that tuple and then I populate a new matrix object and then I return that matrix object. Okay, so does this work? Let's see if this works. Where are you? Run. Oh, yeah, run. Okay, and so there we have 1, 1, 2, 1, transpose. Yeah, that's the transpose, all right. Okay, so that works. But that seems like a long-winded way of saying what I want to say. So what if I short-circuited this? What if I grab this and put it here? And then I don't need this line at all. Oops. Let's run that. Yeah, that does the same thing. Okay, so that's one less line of code. Now, again, it seems a little weird to assign the matrix, but I tried, right? I tried to do that. Oh, okay, now it's like it's not complaining. Let's run this again and see if that works. Oh, yeah, that worked too. Okay. So I thought I tried that and it didn't do it. It was complaining about something. Well, it's no longer complaining, so I guess I'm okay. So I take a matrix, I want to return a matrix, so I'm going to take the matrix and then, except, right, I need to reverse this to 1. All right, run that. There we go. Now it's actually correct again. Okay. So, all right. So we can assign them to temporary variables, or we can just go directly here, but there's no way to iterate through this because this is, the name of this is .0. So just like over here in the pair, it was .1 and .0. So we have to do it like this. So that means, but I guess it makes sense because we've defined matrix to be a 2 by 2, or we've defined the matrix to have 4 values that we're treating as 2 by 2. So a 3 by 3 matrix, we end up with a different structure that says it's a 3 by 3 matrix. So I'm kind of wondering about generic stuff, how we're going to deal with generics if this is the syntax on a tuple. But it kind of makes sense. I mean, if I think about tuples in terms of what I'm allowed to do in C#, then this all makes sense to me. All right, so let's move on from here. That one kind of works. So file, close the folder. Okay, and then back to here. All right, we did it. We got the transpose. All right, arrays and slices. Okay, an array is a collection of objects of the same type stored in contiguous memory. This is an interesting statement, contiguous memory. Arrays are created using brackets, the square ones, and their length, which is known at compile time as part of their type signature. So T semicolon length. Okay, so that's how you specify a length. Slices are similar to arrays, but their length is not known at compile time. Instead, a slice is a 2-word object. The first word is a pointer to the data, and the second word is the length of the slice. A word size is the same as U size. The word size is the same as U size, determined by the processor architecture. Example, 64 bits on an x64. Okay. Slices can be used to borrow a section of an array and have the type signature ampersand square brackets T. So I think borrow ampersand. I'm not sure what this borrow thing means, but I think that ampersand, because in C, ampersand meant address of. So if you had a variable like x, which was an array, you could say ampersand x, and that would give you the address of the first element in the array, and then you could do whatever it is you wanted to do, iterating across the memory, because that would give you a pointer to memory, and then you could, do whatever you needed to do to the memory, which was handy. When you wanted to initialize something, let's say you had an array of, back in the old C days, strings were 1 byte, because it was only ASCII. So, but in larger processors, it's more efficient to write 4 or 8 bytes at a time. So you could view something as a string, say, give me the address of the first element of the string, and then say, well, actually, what this really is, how I want to deal with it right now is as if it were an I32, and let me write zeros to it. And then, because you were doing that, you could, instead of writing 4 zeros, you would write 1, or 4 8-bit zeros, you would write 1 32-bit zero, which is effectively 4 times the speed when you're trying to clear an array, for example. It is also dangerous because if your array of characters in your string is not a multiple of 4, then you've just overwritten something at the, in the next memory block. So not so great if you're not careful. Anyway, that's an aside. So let's have a look. What do we got here? We got slices. So this is going to be, we're going to play around with this a little bit, I think. So let's grab this code. Okay, there's nothing. What's next? Oh, nope. Okay. Yeah, so this is kind of boring because there's nothing to do here. So let's make something to do. Let's copy this. Back to here. File. Oh, no. Terminal. New terminal. What are we going to do? We're going to, cargo new. Okay. And then file, open folder, Rust, array2, folder, source, main, Control A to select all, Control V to paste what we just copied. And there we go. Okay, let's save this and we'll run it. Okay. What have we got here? First elements. Okay, we've got. Okay, it looks like it runs. So I noticed an underline down here. What's going on? Oh, here we go. Xval, unknown word. So I have my C spelling checker running, and it's complaining about Xval. Because normally, because with C, actually, C spell is pretty good about spelling checker for code, and so it would expect camel case, and then it wouldn't complain anymore. But somebody else is going to complain, so I'm going to make it snake case here, so that it satisfies both C spell and it satisfies the snake case guy. All right. Now we got that out of the way. Analyze slice. So a slice, which is of type ampersand I32. So we can look at slice 0 and the length of the slice. All right, fine, whatever. All right, what's going on here? So fixed array. So we say semicolon 5, and that says that's how many elements we have. fixed size array. The type signature is superfluous. Okay, so let's make sure that's actually true. So if I delete this, what am I going to get? I32 semicolon 5. Yes. So that's actually true. So by default, if you remember, right, our data types, by default, if we just put an integer there, it's going to be an I32 unless we specify otherwise. Now, I'm curious though, if I said I64, whoops, I didn't mean to select the whole thing, I64, what happens? Oh, okay. So if one of them is I64, then all of them are I64, still length 5. Okay, that's kind of cool. That's interesting. All right, let's take that away and put it back. And then it's an I32 again. Okay, all elements can be initialized to the same value. So we have ys, we have 500 of 0. So 500 I32s whose value is 0. Okay, so indexing starts at 0. That's like any normal programming language. I think Visual Basic is the only one I know of that starts at 1, or maybe Python. Anyway, like the normal programming languages, we all start counting at 0. If your language doesn't do it, you're just weird. Second element of the array is 1, right? So that's kind of the standard way of doing things. Length is the number of elements in the array. Arrays are stack allocated. This is interesting. Arrays are stack allocated. All right, so there's 2 blocks of memory that your code typically has access to. That's heap memory and stack memory. The heap memory is kind of this big pool of memory that your whole application has access to. And typically there's an allocation and a deallocation that happens over there, and the whole point of Rust. So if you have like Java or C#, what you'll have is a memory manager. When you say, I want to create something of certain size, it will go and create that, allocate from somewhere, from heap usually, a block of memory, and say, okay, this block of memory is for you. And when you're done with it, is there are no more references. So what happens is if you make a reference to a block of memory, then there's something in the background that tracks that. And so when that counter goes to 0, it's not exactly like that, but we can interpret it be that way. Let me just slide myself. There we go. I just want to float above the edge there. When we allocate, we're finished with a block of memory, and like I said, when finish means that nobody is referencing it. So when the reference count gets back to 0, then at some point the garbage collector comes along and says, oh look, there's a bunch of memory here who's no longer being accessed. Let me put it back into the pool of free memory. And that generally works pretty well. The problem is that that code has to run every once in a while. And one of the problems, at least in the early days of C# and Java, was that code would run at kind of the most inopportune times. And so, it was always said, don't write games in C# because you never know when the garbage collector is going to run, and suddenly your frame rate's going to just die completely because all the CPU is going to be sucked up by the garbage collector coming along and cleaning up memory that you've allocated. There's a number of ways of getting around that, and it's still kind of an issue, but not as much of an issue as it used to be. I think they've gotten better with their garbage collector and their scheduling, and people have gotten better at figuring out ways around it. But in any case, in this model of the world, the Rust, it's on us there's no garbage collector to run around and collect stuff. We're kind of sort of responsible. And one of the ways to be responsible is if we declare a local variable like this, and we say we want 500 I32s. So that's 4 bytes each, so 2,000 bytes. So we want 2,000 bytes of memory. You say, okay, let's put that on the stack. The stack is the other place that you can allocate memory to. And typically local variables are put on the stack. And what that means is that the stack is used to keep track of where you are in the execution. So if you make a call to a function, then what happens is the return address from where you called the function, the next instruction after the call, is stored on the stack. And then any parameters that you want to pass are also stored on the stack. And then an additional block of memory is allocated on the stack that says, okay, here's this block of memory that you can use. And typically the compiler will figure out, oh, you want 2,000 of these, you want 20 of those. Let's leave room for that on the stack. And the reason you want to do that is because then when you're done, when it stops executing and you return back to the main piece of code, the stack, basically the stack pointer points back to the return address that you put there originally. It skips over all that stuff and it goes back to the return address, and then once it jumps back to that location in the code, all of that memory that was allocated for your method or your function is basically freed. It's automatically freed because the stack pointer now is saying anything past me, it's usually considered above me, is free space. And so the next time you make another call, you can allocate stuff on the stack and it will use that same block of memory that the previous function used. Now, that actually is kind of interesting because you kind of have to be careful, because that's one of the ways that you can sometimes cause information leakage, right? Because if you allocated something on the stack, something that was a secret, like an encryption key, and then you return, then that encryption key is still there written in memory. It's just considered free. But if you were to have some malicious code that said, oh, okay, I know that encryption key was written there, let me declare a variable, local variable, that occupies that same length. Now, and I won't initialize my block of memory, then cool, I can now read what was already there. So now my function can read the encryption key that the other function put there but didn't clean up after. It would appear though that here we can't do that, because can I do this? Can I just say that? What's this? This says binding declared but not initialized. Okay, so that's complaining, but is it going to let me run? Oh yeah, so it says, hey, error, I used YS that isn't initialized, so it's not actually going to let me do that. Right, could not compile. So it's not going to let me. So I need to initialize on the way in. Now the question, I guess, is that, well, fine, it doesn't let me initialize on the way in, but does it clean up on the way out? Because that's really the where the problem is, right? So if I write code that initializes on the way in, then I'm guaranteed a particular set of values in the array before I start using it, which is cool for my code. But I've populated it with some data. Now I go to if I go to look at the stack afterwards, is there remnants of that data or not? And that's kind of what I wanted to know. I'm not sure how I could figure that out. But anyway, let's carry on here. Okay, so we've got indexing starts at 0, lengths, size of, array occupies whatever bytes. So actually, let's just run this again. So, right, array occupies 20 bytes. Again, that makes sense, right? Because we have 5 integers, i32s, and the i32s are each 4 bytes, so 4 times 5, 20. And again, if I say i64 on this one, and let's see if I can run this. Oh, nope. As analyze slice is expecting an i32. Let's change this to 64. So they've got a match. Oh, what's this? Oh. This other one needs to be I64 as well, because I'm doing that. All right, run. Okay, so here, now, there we go. Array occupies 40 bytes. So when it was I64, they're 8 bytes each, so 8 times 5 is 40. And when it was I32, it was 4 times 5 equals 30. So it occupies that many bytes on the stack, it would say. Arrays are stack allocated, so on the stack, there's that many bytes are being used. This always scares me because back in the day, the amount of stack space you had was fairly limited. And so you didn't want to put too much stuff on the stack, because you'd run out of stack space, and then you'd have a stack overflow, and there you go, and then your program would just crash. But I guess these days with these processors, we've got as much basically infinite amounts of stack space. So for most normal things. All right, so let's put this back to 32. Okay, there we go. We're back to there. So analyze. Oh, borrow the whole array as a slice. Analyze slice. Analyze the slice section. Okay, so this was this slice business, right? So we've got the whole thing, ampersand, and this borrow and the ampersand thing. So what the heck is going on here? So this is ampersand I32. So there's excess, and then we're going to pass in ampersand excess. What if we just pass in excess? No, can't do it. What's the complaint? Consider borrowing here. What does that mean, borrowing? All right, I guess hopefully somebody will explain this to me. What are we borrowing? I think what they're talking about with borrowing is this whole memory management business, because there can only be one owner. And so we are borrowing the ownership. So analyze, we're borrowing the ownership, we're passing it into analyze slice so that it can manipulate this and work with it. And then once it's finished, we've stopped borrowing, and then we can do some other things. Okay. So here we're borrowing a little bit of it. All right, whatever. Okay, example of empty slice, empty array, empty array. Arrays can be safely accessed using get, which returns an option. This can be matched as shown below or used with expect if you would like the program to exit with a nice message instead of happily continuing. What? What's this match thing? What's going on here? Get. So we see 1, 2, 3, 4, 5, slow down, 5 is too far. So we have a for loop where we're going from 0 through the length plus 1. And I think we're doing the plus 1 intentionally to go too far. And so when we get to index 0, 1, 2, 3, 4, and I would guess that the length is 5, but so typically, so we go 0 dot dot up to but not including 5, right? That would be a typical way to do it. The way you would write a loop is you would go 0, 0, 1, 2, 3, 4 if the length is 5. And so if we were writing in a different language, it would be for I equals 0, I is less than xs.length, I plus plus, right? So you would do something like that, and always the less than length. Because the important thing here is that off by one errors are a fairly common set of errors when you're writing loops. And so anything that will help you make sure that you are not off by one is going to be helpful. So here we're demonstrating this get, and it's getting that index, and it's either going to return some value of type T, or it's going to return none, because that's what get does. So let's see, get returns an option, and get returns an option, and an option returns either some or none. Okay. And then we can use this match syntax, which is kind of like a switch statement, to either print that we got it or print an error. This is the error condition. Hey, we didn't get an element that went to, we didn't get an element of that size. Okay. And then I is a U size, and get takes a an index of type I. Slice index, where I slice index self. All right, which I guess is U size at this point. Okay. All right. Cool. And so this says out of bound indexing causes runtime error. So if we did this instead, so save that, and we run it. Ooh, error, could not compile, index out of bounds. So length is 5, but the index is 5, right? So you can't go to index 5 because we're zero-based index. So it just knows that that's an error. Compiling error, this operation will panic. This operation will panic at runtime. That error could not compile. Okay. So we can't do that. We won't let us run with a bad index. That's nice, actually. Yeah, but we can kind of slip in to creating an invalid index by doing something like this, accidentally or on purpose or otherwise, right? Where we try to get an array element and we can't get it. So the get function is kind of, I mean, this, if you're not sure that you can, you know, if you're positive, then you can just do this reference like that. But if you're not sure, then you can use the get and catch the error if something goes wrong. All right. So I have a couple of things. I wonder. So let's save that. All right. So I'm wondering about populating arrays. So these two arrays, we have X and we have Y. And what I want to do is I want to write a loop. I'm curious about this. Can I populate this into there? All right. So what I want is I want to so for what's that? Sorry, I gotta scroll down. For I colon in, right? For I in XS YS I equals I. So I just want to initialize the first, you know, the 1, 2, 3, 4, and 5th element. I want to initialize them to 1, 2, 3, 4, 5. So the 0 element is going to stay 0, and then the next 5 elements are going to be 1, 2, 3, 4, 5 in Y. All right, what's going on here? What's the complaint? Oh, expected a block. Okay, so it looks like I can't, one-liners cannot be by themselves. I have to do the brackets, and so this I think is more standard. Actually, if I do this, and yeah, it'll reformat it. Okay, all right. So we have that. All right, let's see. But I've still got a complaint. What's this? The type cannot be indexed by I32. The trait slice. Oh, okay. The third one maybe is the key here. The trait slice index T is implemented for usize. So, all right. So I is an I32, and the indexing here, because we saw that down here, the indexing is usize. Oh, and I could have done this. What is this? Oh, that's interesting. Just XS. So just 0 dot dot. Okay, we'll do that. No, still not happy. So this is okay. So here we go. So now that I did this, so the length is, this is okay. So the previous one, XS, that one, what I have is I think I'm getting the values 1, 2, 3, 4, 5, and then I am trying to write them into here, and so this is supposed to be a usize data type, and this is not, okay, and this is an I32. So, but then when I changed it to the other one, hang on, 0 dot dot XS dot dot length. Now that one, let's save that. So now this is usize, and it's supposed to be, oh, okay, but I actually, what I want is I want excess I, right? All right, oh, now the whole thing's a problem. What's the problem? Scroll down. Oh, consider changing this to be mutable. Mut is. Okay, mut. Okay, there we go. So, okay. So when I have this, what this is giving me is the index. So as a usize, 0, 1, 2, 3, 4, 5, right? And so, but this one, but that's going to start at 0, which means instead of being 0, 1, 2, 3, 4, 5 as the first 6 elements, I'm going to end up with 1, 2, 3, 4, 5 as the first 5 elements. And so I think what I want is +1, right? Because then I will have ys being the 0th element of ys will be stay 0, and then the next one will be right, I'll take the numbers 1, 2, 3, 4, 5, and I'll place them at elements 1, 2, 3, 4, 5. All right. Okay, so so if I did it, let me do it a second way. For I in excess ys I equals I. So when I try to do this, this says, sorry, that needs to be a usize. So what I was doing here was I was taking the number, like the 1, and trying to make it an index, because this was 1, 2, 3, 4, 5. So I said I want 1 at 1, 2 at 2, 3 at 3, 4 at 4, and 5 at 5. This version, it writes it, it copies the integer, the I32 here, into the I32 there. And then this, the for loop, is using all indexes or all usize things. Here, I'm trying to convert this I32 into a usize. So let's see. Let index equals I dot into. So this into thing converts this type into the usually inferred input type. So, but it's not doing it. So okay, let me do this. Usize. So I'm saying I would like this to be a usize, and I'm still getting it. Am I getting an error? Save. Okay. Oh, and this should be index. Okay. So I would like to convert I. Okay. So I'd like to convert the type I, which is an I32, into a usize. And why is it complaining? The trait bound usize from is not satisfied. The following other required for I32 to implement into usize. Required by a bound introduced by this call. So this is some weird error message. So, I mean, I'm not sure why it would be a problem, because honestly, the I-32 required by a bound introduced by this call. The trait bound usize from is not satisfied. The following other types implement trait from. So it's from, and we're doing into. From. What's from? That doesn't make any sense. All right. So this is where I'm going to cheat a little bit. Well, that still doesn't make any sense to me. The trait bound usize is not satisfied. All right, so no, that doesn't work either. What are you complaining about? What if I just did, can I do that? Can I cast? Syntax error, expected semicolon. All right, so that we can't do that casting thing. How about as usize? Oh, ooh, I think it's happy there. So there we got casting. So I as usize. Pointer size unsigned integer type. The size of this primitive, how many, for example, in a 32-bit target is 4 bytes and a 64-bit target is 8 bytes. So, all right, so we finally, there's all these different, there's like an into, which I'm not sure why, I mean, into claims to do conversions, but it didn't in this case. It said, I don't know how to do that. But this as appears to be, and in other languages we might, do a cast like that, but that doesn't seem to be a thing here in JavaScript, in Rust. But this as, which is familiar from C#, there's some as syntax there. The as syntax in C# does some interesting things because it will initialize this thing to the default value if it's not actually, oh no, that's different. Sorry, I'm thinking of a different thing. Never mind. Ignore what I just said. All right, let me run this just to make sure that it actually runs. Yeah, it does. Okay, it ran. Now ys, the first analyze slice. First element of the slice. When we do the ys. First element of the slice, 1. Because index, oh, right, no. Well, okay, what's going on here? Because the first index of this, oh, but this, because this is 1.4. So it's not actually taking the 0th element. It's taking the 1th element, and the 1th element is a 1. So that actually is correct then. So the first element of the slice is that, and the slice has 5 elements. Oh, here we go. The first element of the slice is 1. The slice has 3 elements. So when we say 1.4, so it's element 1, element 2, element 3. So it doesn't include 4. So whenever we do this dot, and that was also true here with this dot length, does not include, so 0, 1, 2, 3, 4 does not include 5. So, so that dot dot thing, you say the number, but it doesn't actually include that number. It's 1, 2, 3. It's up to, but not including that last number. Non-exclusive. Okay, and it didn't really matter. I don't think it really mattered. So let's actually set a breakpoint here. Set a breakpoint here. And we will debug. Where are you? Debug. Okay, there we go. Yes. Okay, generated that. Cool. Okay, so here, ys is all zeros. And now, as we step through this, there it became 1, the second one, the first element 1, the second one became a 1. I'm just using F10 to step through. There's 3. Okay, and then we pop down here, and ys is now 0, 1, 2, 3, 4, 5. And then here, we're going to do the same thing. Can I change this? Yeah, I think I can go back to 0. Oh, could not set. Why? Oh. No, I don't want the hex editor. Inspecting binary data requires the hex editor extension. No, it's okay. It's okay, I don't need to do that right now. Okay, but it doesn't appear that I can go and modify this with the debugger, which is unfortunate. Because this loop will do exactly the same thing, so we won't actually be able to tell that there's any changes because this will have done. So let's restart. Can I set next statement? Jump to cursor. So it's all zeros here. Okay. And now F10. Okay, and sure enough, there we are, 1, 2, 3, 4, 5. Okay, so that did the same thing. So a couple of things. Mut makes things mutable. The error message told us we needed to make it mut. We've got this approach which gives us a usize index which we can then use to index into the two arrays. This approach gives us the values which we can convert into an index by casting it to a usize. Now, do I need this? And I do not. I do not. Because as soon as I said as usize on this side, I didn't need to say usize on that side. But I couldn't say usize. I couldn't say just this. Because that says, hey, that's not a usize and you're trying to assign it to a usize. Huh? Well, that's weird. That's a weird number. Why is that number? What is that number? Wild. Huh. Anyway, forget it. We don't care. So let me put it back to what works. That works. That's the most straightforward way of saying it. Is that we're going to take this thing, this index, or this int32 value that we've got here, and we're going to cast it to be a usize, assign it to a usize, and then use it. Now, maybe, all right, so let's try one more thing. Can I do that? I think I can do that. All right, and let me just stop and run. Yeah, that still works. No crashes. Okay, so we can do this as well, right? Directly. Say, hey, well, take the I, convert it to a usize, pass it in as the index into an array, and then off it comes. Okay. All right. Now, one last thing. What if I wanted to assign the value I just there, like that? Will it do it for me? So I save that. That's going to be an error. It's going to say, hey, this is a I32 array, and you're trying to assign a usize to it. So can I say I as I32? Oh, yes, it will let me do that. Okay. Now, the only danger of this approach, is that if the length was really, really, really long, then potentially we could end up with, because usize is 8 bits or 8 bytes, and an int or an I32 is only 4. So if we ended up with something over 2 billion, which would be a really, really big array, but I suppose it's possible. If we were manipulating a file, for instance, a video file that's larger than 2 gigabytes, then we could end up in a situation where it would overflow, and we would have a problem, because that as I32 wouldn't work anymore. So I think there's one other way, and this was how I was typing before. So let val equals I dot try from dot. Okay, so then so what's this? Try from. No method name try from found for the type usize in the current scope. Hang on. Use the associated function syntax instead. Usize : try from. Disambiguate the associated function for the candidate usize as try from. Try from. Quick fix. Well, I need to put I in here. No? Okay. Mismatch types. Expected I32 found enum opt usize. Oh, this is an option. So this returns an option. So so what this is doing is it's doing a test. It's saying, is it and this is where I'm cheating a little bit, because I kind of struggled with this the last time I recorded this thing. So this try from returns not an int32, but it returns an option object. And down here, this thing also returned an option. And so there's this match syntax that we can use. So let me do this. Let me say, let's see, opt. And we'll say, and then match opt. What's the syntax? Yeah, it was match the thing, curly brackets, and then sum none. Sum I32. Hang on a second. Okay, some option I32. What's the syntax? Double fat arrow, and then we're going to do something. So fat arrow. ys I. Oh no. Yeah, I plus 1, because that's a U size, but I want to write, this, x, no, comma, none, print line, too big. All right, so that's another way of doing it here. This is more a safer way of doing it, because, you know, if we went over the top, we would say, hey, we've got this, we're going to convert this U size into an I32, and I'm not sure what this OK thing is, but I think try from returns a result, and OK converts that result into an option, and then we can use the returned option and then go with the sum none business. So if it is an I32, we will assign it, and we'll give this the name, instead of x, val, and then val. Okay, value. And then if it's none, then we're going to say, oh, that index was too big to fit into our array, for instance. Okay, so that'll do it. This will also do it. It'll do this. So it's funny, because this line of code, this block of code, and this line of code do the same thing in most cases, but the block is safer, because it handles indexes larger than signed I32. Okay, so that's, we can, you know, again, most of the time I would think that you could just do this and it would be safe enough, right? But probably, I mean, if you really want to write safe code, then this is your best bet, is to, when you're doing conversions, not to depend on the built-in thing. Because I wonder what it does. if the number is actually too large, what does it do? So if I did something like let q u size equals and then I said ys 0 equals okay, so at compile time, or at save time at least, so let's try running this and see what happens. Run. Oh, well, that's interesting. It worked. So what? All right. Now I want to know. Let me debug this. Okay, what is ys0? Oh, it truncated. So, all right. So I guess it's safer because q is this really big number, and y, the element 0, is this number, which presumably is the low order 32 bits of this really big number. Interesting. Interesting. Okay, so it's truncating it. It's not throwing an error. It's truncating the value. So that actually can be its own set of danger, right? This, again, even still, this will be safer because if it overflows, all right, well, now I'm curious. What happens if I do, well, let's just copy all of this. And put it here. And there's no I, but we're going to go Q. And then this is going to be 1. This value, okay. So let's set a breakpoint there. Oh, save this. Set the breakpoint there, or there. Let's run this again, debug. Oh, something went wrong. Linking with link.exe failed. Oh, stop. All right, I think it's because I debugging. Okay, that worked. All right, so let's see. So we wrote the truncated thing. So let me just step F10. We're doing a none. Too big. Okay, so that kind of definitely, right? If we do the as and it's too big, then we're getting the truncated value and we're storing that, which is not the value we wanted, right? It's some weird subset of the value we wanted. On the other hand, if it is we use this option approach and the try from, then we're going to get a positive error message that says, no, you can't do that because it doesn't fit. So that's handy. And it depends, because like I said, sometimes overflow is okay and you don't mind it overflowing, but sometimes you do want it to notice that it overflowed and do something about it. So there you go. Okay, I think that's enough for today. Thanks for listening, and catch up to the next ones, and the next live thing I do will be kind of skip further ahead. All right.